Hi, I'm Ben-Yaakov. This presentation is entitled A Deeper Look at the Approximate Design of Power Inductors with Gapped Ferrite Cores. And it includes an example, a worked-out example with some numerical values. Now, let me say a few words about the motivation of this tutorial. In the background, we do have many calculators which are offered by vendors in order to calculate the core required for a given inductor. You feed in the information about the inductance, the current, the frequency, etc. and you get out the cookbook, just the final value of the core, the number of turns, etc. So if we do have these calculators, why do we need to bother about understanding how to design a core? Well, I personally think that a good designer should know exactly how the device he is using is constructed. So the objectives here are really to gaining a better understanding of magnetics in general, also double checking the automated calculation done by the calculators. At times you'll find that you can improve on it, or maybe the design is either limited or maybe too dangerous in fact. Also provide flexibility if you like to change a core, you like to go to another vendor, another shape, so you can do that. And in particular, this tutorial is for people who like to do it themselves and wish to have a close check of the components that are used in the design. So what are the problems we are facing when you're going to design or select a core and design an inductor? There are two issues here. One related to saturation. We have to make sure that the core will not go into saturation. So this is one aspect. Another aspect is that we don't want the losses to be higher than a given value, because the losses, first of all, of course, lower the efficiency, but also they heat up the inductor, and the so-called hot spot might get, the temperature might get too high. This will damage insulation. Also, it can actually bring the core into a dangerous temperature. So we do have this information about how this core is, or this inductor is supposed to work, and we have to worry about these two very basic limitations. Now usually we are given the inductance, the peak value, the delta I, the ripple of the inductor, of the current of the inductor, and the frequency. This is from the design for the inverter or converter or whatever circuit we are working in. I'm mainly talking about switch mode converters and resonance. So from this information we have to select a ferrite core and a wire size such that the B will not exceed a given value, and that the core losses will not exceed a given maximum value, and also that the copper losses due to the resistance of the wire will not exceed a given value. All these subject to a requirement that we would like to fill up this window area as much as we can. This is the winding window here. This is where the wires are put in, and in order to make use maximum of the core, we like to fill it up, or select a core, the smallest one, that we will be able to fit in the wire. Here, of course, it's very wasteful. We have only one layer, and if we could have filled up the window, then of course the size of the core that we would need would be smaller. Notwithstanding some other issues that I am not discussing in this tutorial, and that is proximity losses due to packing of wires, one close to the other when they are carrying current. So this is a subject that I'm in this tutorial not covering. So the overall procedure will look something like that. We have the requirement, and here we have a first round of the approximate design, and this is what I'm going to discuss in this tutorial. Then we check to see the result, And if they are okay, then that's it. If not, then we iterate. In fact, usually would mean that making the core larger and then go throughout the design again. Now, when it comes to the peak of the magnetic flux density, we look at the hysteresis curves, which are provided, of course, for each material, and we have to decide up to what level we would like to go, really the peak value of the magnetic flux density. Now here shown are two curves, one for 25, and as you can see, temperature has quite a bit of an effect. This is, by the way, an expanded scale here, and then the scale here is different. We set up the value that we want, say in this case 300 millitesla for this particular material would be the maximum that we would like to go at, given the current and the inductance, etc. Knowing this value, I can then relate it, this peak value that I decided as a limit, I can relate it to the peak value of the current that will cause it. And this can be done by looking at this relationship, expressing voltage as a function of the BDT and the IDT, and then taking the integral of both sides from here 0 to the peak value, here 0 to the, again, the peak current value, and I come up with this equation. This equation relates the maximum magnetic flux density to the inductance. Now, we have to realize that this is all approximate, because when doing this integral, I am assuming that L is constant, which is incorrect. In ferrite, it's not so bad. In powder core, it's much worse, but in ferrite, we still have some variation of the inductance as the current goes up. So again, this is a first order approximation. So now we go to the delta B limitation. The delta B, or the variation of the flux density, is causing losses. And based on the Steinmetz equation, which I'm not showing here, which is a power equation, we can draw these curves. These are actually approximated curves. They are fitted curve or fitted to a data curve. And this is a log-log scale, and since this is a power equation, then it becomes a straight line. So in here we see the variation in the magnetic flux density. This is the peak value, and it relates to delta B over 2. Again, it's an approximation because this is measured small signal with no DC, and we are assuming that it is valid for a non-sinusoidal waveform and also with DC. And here we have the power loss. This is here shown at kilowatt per meter cube, which is equivalent to milliwatt per centimeter cube. And we see here curves for different frequencies. The higher the frequency, the higher the losses for a given B hat. Okay, say for this B hat, we have this one, we have for 25 kilohertz this loss, and then it goes up and up and up as the frequency goes up. Now, we have to decide on a number that we would like to start with. This will be the first step, and then we may wish to iterate on it, but we have to give it a first guess. And a good starting point is 100 milliwatt per centimeter cube, which translates to a fairly reasonable increase in temperature. We'll talk about it a little bit later. So this is something that we assume at the first stage, and then we can iterate on it. We have this limitation of power from which we get the delta B. That is, once I decided on this limit and then I know what is the frequency, then this will determine what is the B hat, okay, and what is the delta B. So I know what is the delta B, And in fact, I can use the same relationship as before, but now I can do the integral between B1 and B2. This is delta B between them. And this will be corresponding to I1 to I2. And I'm getting this relationship. It's very similar to what I got before, except that now it's for changes. That is, delta B is L delta I, and this is the cross-section area. This is the cross-section area of the core. Here, this is the cross-section area, which at this stage, I don't know yet, okay? We're going to go around it by deriving a parameter that will allow us to choose a core, and then we will know what is this area for the chosen core. Now, what about wire losses? The wire losses are a function, first of all, of the conductance, the resistance of the wire, times I square, and this is related to the current density that we allow. That is how many amps per millimeter. This should be square, okay, square. And then we have also proximity effect. There's a packing of wires one beside the other, and then therefore the magnetic field created by one is affecting the other one, and then we have a higher AC resistance, and also magnetics feel like if the winding is near a gap. These two are important, but being a primer on the subject, I'm not going to discuss it in this tutorial. So we come now to the very important parameters, AP, area product, which is the product of the cross-section area of the core times the window area or the winding area of the core. Our objective is to select a core such that the losses will be as we decided, and the maximum magnetic flux density will not be over the limit, and then we like to fill up this area so as to optimize the design. So we have seen this relationship already. J is the current density in IRMS divided by area, cross-section area of the wire, of the single wire here. And we can then express the area of the core, or the winding area I should say, as the number of wires with cross-section A sub D divided by K. K is a filling factor, which means that it takes into account the fact that you cannot fill up all the area with copper, because first of all the wire is round normally, and then there is a distance between them, and also it depends on the type of the wire. A Litz wire will have a K small because the packing is smaller. So this takes into account the filling factor of the winding within this window. And from this we can get that the cross-section area of a single wire is the IRMS over J. And then the number of wires then there'll be in this window is this number here, and replacing the cross-section area of the wire with this expression, we get this expression for the number of turns that we can put into this window of a given core. So we have this equation, we have the number of windings, so we can now put this expression instead of n, and we come up with this equation, and then we can look now, we have here the area product, A sub E times A sub W, the cross-section area of the core times the window or winding area window, and from here we get then that this product, the area product, is equal to this very important term. Now this expression here came from the integral from 0 to the maximum value of the magnetic flux density. Obviously we can do the same thing from B1 to B2, and in this case we are going to have another expression which is similar to this first one, except that here we have delta I and here we have delta B. So we have now two expressions for the area product. And depending now on the value of delta B and delta I, or we can put it in a different way, we can compare this to this and then dividing out all the common term, we can find that AP1 is larger than AP2 if delta B over B peak is larger than delta I over I peak. So we get two numbers, and obviously in order to be on the safe side or be able to comply with all the requirements, we have to take the largest value. Now the largest value now will depend on actually delta B. If delta B is very small, then this will be the largest value. And delta B will be small at high frequency. We'll see it later on. So at high frequency, this expression will be dominant. So what are design steps? We start with the requirements: L, average, I peak, I RMS, switching frequency. We select a ferrite material. We set peak value of the magnetic flux density. We set delta B based on the desired core losses. We assume, this is misspelled here, J and K. We calculate AP, select the largest one, and then from IRMS and J we calculate the wire diameter, and then calculate the number of turns, estimate the gap length, and if required, adjust the gap length by measurement, by experiment, to get the required inductance. And then we calculate the losses to see if we hit the target, and if the losses are too high, then we can iterate, go back, assume a larger core, and go through the process. So what about the ferrite material? There are many ferrite materials available. Depending on the operating frequency, obviously we would like to get a material in which has the lower losses at our operating frequencies. So suppose we work at, say, 100 kilohertz. I'm showing here two material. This is a Ferg group. This is just an example. And you see that in the case of this material, 3C81 for 100 kilohertz, 100 millitesla, the power loss is 200 milliwatt, this is a kilowatt per meter cube, or 200 milliwatt per centimeter. This material, which is a high frequency material, for the same delta B, I find that for 100 kilohertz we have much lower losses. It's only, what is it, 2, 3, 4, 5, 60 milliwatt per centimeter square. So it's more than a factor of 2. So therefore, the selection of material will depend on the losses. Now, also one has to take into account that most ferrite materials losses are temperature dependent, and then you have to decide which is the estimated temperature that you're going to work at, and take this also into account. What we see here is for 3F3, here we see that the frequency makes a big difference, of course, for the same millitesla here and here. For 200 kilohertz we have a higher losses, which is what we have seen from the other graph, or the Steinmetz approximation. So once we have AP, we can proceed. Let's have a look what is given. We know L, this is from the problem we have, I peak, I RMS, B peak we have decided on, K we estimated depending on what type of wires we expect to use. The range could be from 0.3 for a Litz wire to 0.7 for a well-packed single wire winder. And for J, we first set a number and then see what are the wire losses, and then readjust it if required. A good starting point will be like 4.5 amp per millimeter square, and then this, from experience, has been shown to be sort of an average number that you'll eventually settle to. Let's take a real example with some numerical values. Suppose we have a inductor which has this type of a current in it, and then we have the average given. The inductance delta I over 2 is 22 amp, so this is 44 peak to peak. I peak is 67 amp, this is this value. This is 22 plus 45. We assume a 300 kilohertz, and I'm starting with a core of losses of 100 milliwatt per centimeter cube. And again, looking up the various materials, I decided on a 3694. Also, there is a question of availability. Not all the cores are available with all material, so it's a compromise here. And I've decided to go from the construction point of view to E core and set the B peak to 300 millitesla with an estimated filling factor of 0.5, and I'm starting with J equal to 4.5 amp per millimeter square. Now IRMS can be found from the average, which is 45, plus this 22, which is delta I over 2 divided by 3, which gives us 46.8 amp. This is the RMS. So since I've decided on 100 milliwatt per centimeter cube, I'm working at 300 kilohertz. That brings this B hat, or delta B over 2, to be 60 millitesla. This is what I have to observe if I want to keep the 100 milliwatt per centimeter cube. So now I'm ready to calculate the area product, and I'm doing it for the two cases, one for I peak and B peak. Everything here is now known or assumed, J and K, and then I'm doing it for delta I and delta B, and I'm getting two numbers. And here is 1.9 10 to the 5th millimeter to the 4th. This is the largest one. So the delta B, being high frequency, is dominant here. So AP2 is the largest, and now I have the task of looking up catalogs of cores and looking for a core that will have an AP area product of larger than this value. So once I know this number, this is the largest one between the two, the area product, I can go into catalog and look up for a core that will fit this number. Actually, the AP of the core has to be a little bit higher than this value. Notice that the shape of the core does not matter. Would it be a regular core, an E core, ETD core, or a flat magnetics core? AP is an AP, and in all cases it's the same. Now obviously the geometry of the core will determine whether the window is large or small. For example, in flat magnetics you have a smaller window, so this will be a case in which the number of turns will be smaller, but the cross-section area of the core will be larger. So this would be better for, say, printed circuit board type of winding. So the point is that one has to decide what is the shape and the family of cores that he'd like to have for its own design. When you look up the catalog, you look for the AP, and AP which is larger than the one that you have calculated. I've done this search for the E-core family and found that this core here, E653227, will fit the build in terms of the AP. Now, in many catalogs you'll find this value already available as is, in actually the bobbin. In the bobbin parameters, you see here the area product, and here we see 2.1 10 to the fifth. We need 1.9, so this seems to be pretty close to what we need. So it always has to be bigger, of course, otherwise we won't be able to put all the wires into the window. And if this number is not given, you can go to the actually core drawing and sort of estimate the area. This is half of the core, so the area here is twice, and estimate this area here. This is the winding area. And of course here we have more parameters like the effective volume and the cross-section area that we would need later on of the core. Okay, it's 440 millimeters square. So now we go back to the question of the wire. We have decided on a J. We know what is the RMS current, so therefore we can find what is the diameter of the wire, which is 3.6 millimeter that we need. We need 10 millimeter square area for the copper. Now, since we are working at 300 kilohertz, we have to worry about skin effect. Skin effect can be approximated for copper at 72 square root of the frequency. This is in hertz, and the result is in millimeters. So we get here 0.13. So we need a wire which is the diameter smaller than 0.26, twice this value. Well, in order to avoid or somehow remedy perhaps proximity effect, I would choose a smaller diameter, say 0.15 millimeter. So this is the wire, and now since we know what is the total area we need, and we can find out what is the area of the single strand that we need, and we find that we need 10 divided 0.017. This is the area of a single strand. This is the total copper area. It's about 600 strands wire that we need. Usually they'll come in bunches of several strands per bunch. Now obviously we go back here. Perhaps with a wire like this, a K of 0.5 that I have assumed, it may be a little bit too high. Probably a 0.3, 0.4 will be a good, better choice. So now from this equation, we can express and the number of turns that will fill up or will be compatible with our calculation. And now we have the cross-section area of the core, so we can put this number here, and we find that we need 17 turns. 17 turns. Now I can go back and check to see if I'm okay. The window area is the number of wires times the cross-section, the total cross-section of the wire, which is 10 millimeter square, and divided by K, which I've assumed, and it comes to be 352. And it turns out from the data sheet, the core that I've selected has 394, which means that everything is okay. I haven't made any mistake. As you can see, everything comes into place if I'm following. We can calculate now the resistance of the wire, knowing the average length of a turn. This is actually from the data sheet. I can also estimate it from the geometry of the core, and it comes up that the total length is 2.5 meters and the diameter 3.6 millimeter for the 10 millimeter square that I need, and it turns out that the resistance is 4.2 milliohm. Now I have a RMS current on 46.8, and therefore the loss, conduction loss of the wire, just the conduction loss, is 9.2 watts. Now I can go back to the core losses. I've assumed 100 milliwatt per centimeter squared. This is how I've chosen delta B. Now from datasheet I have the volume to be, here it's millimeter cube, I need it in centimeter cube, so it's 79. And since it's 100 milliwatt, we have 7.9, and the total loss is 17.1 watts. We can estimate, there's a experimental equation, you might say, that from which you can estimate the hot spot of a magnetic structure, like an inductor or a transformer, and it is based actually on measurements that were made on E-cores. It's very well known in the industry, and this equation says that the increase in temperature from the hot spot to the surface area, the ambient, is approximately given by this equation. This is P, the total loss. This will be in milliwatts. A is the area in centimeters squared. Total area means that this area, this, and below and on this side, that is the total surface area of the structure. And delta T will be in temperature rise in degrees centigrade. So now, from the core geometry, I estimate very sort of approximately the area, surface area. So I take this area here twice the E-core, twice, and then all the sides. And I come up with this area, and we have in milliwatts 17,000 milliwatt total power loss. And I come up with a delta T of 45 degrees centigrade, which is pretty good. Say if the ambient is 50 or 60, then we are in good shape. So now we have to adjust the gap. We can estimate the gap length by the following way. An inductance is equal to the inductance of the inductor is equal to the number of turns square, mu, cross-section area of the core, and the magnetic length. Now, the relative permeability is approximately, for cases in which the permeability of the ferrite is very high as compared to air, the relative permeability. So the relative permeability of the structure itself, not the ferrite, but that's just the structure, will be the length, the magnetic path length over the gap length. So I can insert this here. So I get that the inductance is equal to n squared mu 0 AE, and the length of the gap, from which I can estimate what is the required gap length, and I find it to be 7.8 millimeter. Okay, this is an approximation. In reality, what you'd like to do is, after you build up the inductor, just to adjust the gap, to measure the inductance until you get the one that you need. Now I can check it against data given by the manufacturer in the following way. I can calculate AL, which is the inductance over n squared. In our case, the required LL is 87 nanohenry per turn square. Now, the vendor is giving this table for this particular core, and you see that we need 87, so here we have 100, which is pretty close. We found that mu E required is 22, but here it says that the gap is 14 millimeter, not 7 as we have found. And if here I'll calculate what is the relative permeability by L sub B over L sub G, I find 10 and not 22. So this again shows that this equation is approximate, and these are actually based on actual measurements and taking into account the fringing effect and the non-symmetry of the core. Turns out that that this estimate that I've done before is really very approximate, just give you a order of magnitude, you might say, and then you really have to adjust it. So we have seen here a case in which delta B was small because I've chosen high frequency just to demonstrate it. And then if, of course, delta B will be high, if the frequency is lower, then the allowed delta B for a given core loss will be much higher. So this number, AP1, will be larger because we'll go into the limit of maximum magnetic flux density and not the delta B. And therefore, we have to calculate it or choose the core according to the largest number, which will be, in this case, this number. Otherwise, it'll be, of course. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you have found it of interest, and perhaps it will be useful to you in the future. Thank you very much.